So I guess what unites us all here is that we're looking at figuring out how to use physical systems to do computation. And the work that I'll share with you today, in this work, what we want to do is use physics to solve the problem of training machine learning models. Basically, what we want to build is strange. No, but also the computer seems crashed, but it shouldn't be crashed, just a slide. Well, now it works. All right, let's hope it stays that way. So what we're trying to build is a machine, here idealized in this way, where we inject samples, for example, encode in the amplitude or frequency of a signal. We then let the system evolve, and because of its autonomous evolution, the system becomes able to perform a new task. Now, this work draws very heavily, for example, on the pioneering work from Sam, I don't know where he is, in realizing local learning rules. But here, the unique point that we are trying to achieve is that we are trying to encode the learning rules in the evolution of the system. So we want to program learning rules in a Hamiltonian. Now, of course, because Hamiltonian doesn't necessarily want to do what you want to do, we have to follow a process of co-design. So we have to adapt our learning rule to be something that the system naturally wants to do. Our physical platform is a network of MEMS oscillators. So this is an example of a MEMS drum. We can apply an electrostatic potential that we can use, for example, to introduce a parametric drive, and then the system goes into self-oscillation. Now, we really like this system because it's extremely controllable. We can measure the motion down to the thermal noise with exquisite resolution. We have very high nonlinearities, which allows us to operate, to do non-trivial work with energy of attojoules. And it's also quite easy to fabricate. So we can make prototypes in 1 or 2 days in our clean room, which allows us to iterate and to explore new concepts very fast. So it's a very nice platform for experimentation. And it's also a generic oscillator platform, which means that the insights that we get from it hopefully can transfer to other platforms. So what I will do over the next half an hour is construct in this platform all the elements that we need to realize self-learning. Now, what we want to do, the problem of self-learning, basically what we want to do is train a neural network, which consists of a set of neurons, and those neurons are interconnected via weights. And the problem that we want to solve is figuring out what the weights need to be in order for the network to do a task. Now, in conventional physical neural networks, making a physical neural network, of course, is a hard problem. But at least we have, in principle, only one type of variables. We have to store the activation, the neural activation at every site. Now, if we want to train a neural network, we need to introduce extra variables. We need at least our weights to be a dynamical variable of the system. And ideally, we need also some credit assignment information, some information that allows us to know if the weights are doing the right thing or if we should change them instead, this weight information. So in those models, when we try to train a machine learning model, if we want to train a machine learning model, we need various types of variables to coexist in our system and to interact in a specific way. So in our platform, this is an example of one of these MEMS devices that we made in our on-site clean room. We can store naturally different variables because those resonators are multimodal. So if you excite them at different frequencies, they have different modes of vibration. And each of those modes of vibration has its own independent amplitude and phase, which allows us to store a specific model variable. So this is very nice because it provides us with a natural way to store multiple channels of information in a same system by storing them at different frequencies. Now, this is very nice, but it presents one challenge. And the challenge is that each of those modes has a similar memory lifetime. So when we have a machine learning model, the neural activations are different for every sample. If we are classifying MNIST digits, every MNIST digit will result in a completely different activation. But the weights need to be remembered throughout the entirety of the training process. And this is something that the system doesn't naturally want to do. So our take is to get the system and introduce a parametric drive. Because those oscillators, those are drum resonators that are separated, they form a capacitor with the substrate. We can apply a voltage to them, and this voltage creates an electrostatic stiffness. So you have electrostatic force between the oscillator and the substrate, And this force is distance dependent, so it produces an effective stiffness. And because it's voltage dependent, we can in principle make it time dependent, and we can drive it at the frequency we want. Now, if we drive it at omega, we'll have an oscillation, a normal resonance. But if we drive it at 2 omega, we get a different effect. We get what we call a parametric oscillation. So if we drive below a certain threshold, nothing happens. The system doesn't move because we are driving off resonance. But at the moment where we exceed a certain threshold, the system goes into self-oscillation. And this self-oscillation has two stable phases that we label as 0 and 1. So we essentially create a synthetic double well potential. Now, what is very nice of this system is that these states are extremely long-lived. Right? So this is an experiment, by the way. You can see already there is disorder. Most of what I show today is experiment. I'll show what is theory. Basically, it has two stable states, and if you end up in this state, you will spend there for a long time. If you end up in this state, you'll spend up for a long time. We can make large arrays of resonators. Here, for example, we made an array of 25 resonators, and then we drive all of them at the same frequency. Our resonators are very repeatable, so we can, with a single pump, get them all in this regime. And then we can flip the phase and store information. For example, here we wrote the name of our institute, AMOF, and this text stood in the setup for about 48 hours until my student got tired and unplugged it because there were no flips going on. We were hoping we would see some flip, but we didn't. Now this is very nice because if we introduce this parametric drive to the system, now we have a long-term memory that we can use to store the weights. At the same time, all other modes of the system don't become slowed down because of the parametric drive. They retain their original frequency. So now this is very nice, but this so far, by the way, this is just to show the repeatability of our setup. This is the excitation frequency and amplitude, and the area that is colorful is the area where we have this bistability. And this is for a resonator, and the area that is shaded here is the overlap between all of them. So we have a very nice overlap area where all of them are operating in parametric resonance. Now, it's very nice that we constructed this because now we have a long-term memory that we can use for the weights, and we have a short-term memory that we can use for the activations and the credit assignment, the gradients, nudge phase, whatever you name it. But that's, of course, not the whole story, because it's not enough to have weights, to have a neural net. Weights is just a variable that is stored somewhere, but is not doing anything. So here, what I'm showing you is, here we have two modes, right? This is going to be our wave mode. And this mode here is the one that is in this parametric oscillation state and can be in state 1 or state 0. Now, this is a computational mode. It's a mode that we're going to use for computation. Later, we'll use other modes, but we can take it as an example. Okay. Now, what we observe is that if we measure the resonance of this mode, this is independent of the weight state. So both weight states give the same response to the other mode. So our weights are not yet parameterizing our computation, are merely being remembered. Now, how can we make our weights parameterize our computation? Well, it turns out that there's an interaction, because our system is nonlinear, there's an interaction between the different modes. For the optics people, this is what's called a cross-care interaction. Basically, when one of the modes oscillates at a certain frequency, with a certain amplitude, it has a longer average length, so it increases the tension of the drum, the overall tension, and shifts up the frequency of the other modes. Now, because both states have the same absolute value of the amplitude, they both shift a computational frequency by the same amount, so they both introduce the same frequency response. By the way, you see there is a cross paper here. This paper came out recently, and it summarizes many of the ideas that I'll talk about in this talk. The ones that are crossed are the ones that are different, because we figured out how to do things better since that paper came out. So this is one thing we're doing better. Now, what we can do in this system, though, is break the symmetry between those two states. And the way we do that is by applying a direct drive. So we apply an oscillation at omega, and this oscillation will go in phase with one of the states, but out of phase with the other. And this has the effect of changing the response to this shape. So now, if we are on the upper branch, our amplitude goes up, while if we are on the lower branch, our amplitude goes down. So when we do that, our computational mode, its natural frequency becomes state dependent. It becomes weight dependent. And doing this, applying this drive, so this is the same lattice, it's just a lattice. There's nothing patterned on it. But because we're introducing those drives, we are able to make the system store weights, and the weights parameterize the other computation. And we can even tune by deciding how much of this direct drive we apply, how much separation we want to introduce to match what we need to do. Now, this is only a binary weight, so that's not a continuous weight. In neural networks, we generally like to have continuous weights. But however, if you build a lattice and you apply an input signal on one side and an output signal on another side, you can, by using different combinations of weights, get different transmissivities, and even potentially, that's probably our IT policy that forces us to have a computer that logs every 5 minutes. Basically, you can get different, for every configuration of weights, you can get a different real and imaginary transmissivity through this device. Now, depending on the parameters, you can get very different configurations of states, and these configurations differ in different things. One of them is the expressivity. So in general, the more spread around that this is, the more expressive our model is, because it can do very different responses. At the same time, they also affect the trainability. What affects the trainability, what is a very good property of this distribution of states, is in general, we tend to like that states with a similar transmissivity, they have similar spin configurations. So it's a very bad thing if you want to move from here to here, and you have to completely change your spin configuration. So, and this is something that we're trying to quantify, how much the similarity or the proximity in the transmissivity of a lattice corresponds to a proximity or a Hamming distance between the spin configurations, because this plays a crucial role in making the system not have to take too many twists and turns before it converges to the correct answer. Okay, so now we have something very nice. We have a system that stores weights and activations. The weights parameterize the activations. And now, to have our fantastic automatic training, the only thing we are missing is that our weights update automatically by the autonomous dynamics of the system. And how do we do that? What we do is, this is a linear system. For now, we're focusing on linear systems. We can represent it as a lattice, right? Every resonator is a site, and they are connected by weights. Then we can apply a certain set of inputs, and we'll get an output that is given by a linear response. And then what we can do is we can define what we want to optimize as a misfit of the output. So we define a function that tells us whether we like or we don't like what the system is doing. And what we're going to do is try to minimize this misfit by changing the weights in the direction of the gradient. Now, we already, fortunately, Romain already introduced this equation for me, so I don't have to go again through it. But basically, you can prove with Wirtinger calculus that in a system like this, the change in misfit equals 2 times the real part, with minus, of some expression that looks like this. So basically, it's the product of 2 things. The first thing is the response of the system. This is the dynamical matrix of the system. We've seen enough adjoint today, so I'm not going to go too much into the details. But this thing is the response of the system applied to the gradient of the misfit. And this thing here is just the response of the system applied to the input forces. So if we want to see how much should we change the frequency, for example, of this side, what we need to do is get the system excited with the inputs, get the amplitude. Get the system excited with the gradient of the misfit on the output, get the value, multiply those 2 things, and if this number is positive, it means that we're going to make our sign go up, frequency go up. If this sign is negative, we're going to make our signal go down. This type of learning rule, by the way, people call it sign gradient descent, because it's a version of gradient descent where we flip on the sign, we don't flip on the magnitude. But this is what we can do in this system. All right. Now, to do this, ideally, we would want 2 copies of the system. We need 2 copies that we compare, driven by different functions, and that we then going to multiply and get the result. Now, this is a place where it's a bit annoying, right? You know, we need 2 copies. They have to be perfectly the same. That is an obstacle to realizing this learning. But here is where my past, we had Cyril was very influenced by his past as a geologist. I am influenced by my past as a topologist, a condensed matter person. So in condensed matter physics, we know that when we have a system that has symmetry, some special mode, so every mode corresponds to what's called an irreducible representation of the symmetry group. And some of those irreducible representations have dimension 2, which means that they come in copies. So there's going to be some modes, for example, these P modes, that are going to automatically appear in copies of 2 as long as we respect the symmetry of the system, as long as the system is round, essentially. So this is very nice because if we input the information in those modes, then automatically the system behaves as 2 copies without us having to do anything special. So that does a very nice work for us. Now, here I like to go on a bit of a tangent. That is that, of course, this system works perfectly well as long as your modes are perfectly symmetric. If your modes are not perfectly symmetric, then as the signal progresses, you get a misalignment between the real gradient and the actual gradient that you are computing. Now, this is very, very similar to how topological insulators behave. So if you have a topological insulator, this system, if you talk to a person who's trying to sell it to you, you're a referee and they're trying to get it published, they're going to tell you it's immune to backscattering. You send a wave and it goes through anything. But there is terms and conditions. This happens only if you respect something called the protecting symmetry of the topological insulator. At the moment where you violate the protecting symmetry, your mode develops what is called a localization length. At a certain length, it's not propagating anymore. And here we have also a localization length. So basically, if this is an accidental degeneracy, so it's a system that we are making it round because our clean room machine makes it round, when we reach the limit of our machine, it tells us how big our neural network can be, otherwise you cannot train it anymore. Now, a few things, we're trying to look for tangent ideas on how to get around this. There's a few of them. So one of them is, for example, rotating between the modes to try to cancel the effect. Another is try to look for learning rules that don't have protecting symmetries like Hebbian learning. Try to see, in topological insulators, there are also insulators that are not protected by symmetries. Maybe something like this exists. Or just trying to use natural symmetries that we can rely on to a high accuracy. But this is something you have to keep an eye on. Okay. So now the question is, can we compute this quantity physically? And the answer is yes, and we can even do it in the lab. So basically, what we want to do is we want to compute the sign of the product between the complex between the real part of the complex. The sign of the real part of the product between the complex amplitudes of 2 computational degenerate modes, one that stores the activations and one that stores the gradients. All right. So how do we do that? Well, you can, in principle, create such 3-particle potential. And if you create this 3-particle potential and you you go to a rotating frame and you put the amplitudes there, basically what we do is we define an extra mode that we call the ancilla, and this ancilla mode will store the result of this product. Okay? So you can then introduce this potential, and this potential multiplies, so the force acting on the ancilla, that is the x sub a, will be the derivative of the potential with respect to the ancilla, so it's directly the product between the 2 displacements. And this term here makes time dependent. What it does is convert it between the frequency of this term, that is 2 omega, because you're multiplying 2 components at the same frequency, and the frequency of the ancilla. If you do this, then you will sit the ancilla with the right product. And what you can do after is turn on a parametric pump on the ancilla. And then if the sign of the real part is positive, you will go to the 1 solution. If the sign of the real part is negative, you will go to the down solution. Okay, so how do we create this 3-particle potential? Well, this is something that we can do. So we can put electrodes in our system, and this is one of our drum resonators. We can put electrodes on it, and because the gap between the electrode and the substrate that is creating the electrostatic force is very small, the electrostatic force is nonlinear, and you get a long Taylor series that contains also second order, third order terms, and so on. And those terms will generate the 3-particle interaction that you need to compute this product. Right? And then to get the right signs and so on, we play with both the frequency to get the right subtraction between the modes and the spatial overlap. Now, an interesting question is the nonlinearity strong enough? So here there is an example where we were playing with this early on. We had a nice drum. We started applying nonlinear potentials, and the drum came too close to the substrate and never came back. So an interesting question is, can we get sufficient nonlinearity that we can do play this type of games without ending up with this type of drama. And well, just a brief positioning of the electrodes, right? So we want a specific product, right? So we want to prevent having cross products. We don't want to have an XA squared and an X gradient squared. So what we do is we can put 4 electrodes in the system, and then apply different signs, and this will kill the X squared and Y squared, and will give us only the 3 particle interaction that we need. Just a bit of a practical term, right? So we tried to do that in the system. This is a preliminary experiment. So here we are not quite doing the full thing. We only metallize the whole drum, and we are using 2 signals, sine and cosine, that we multiply together, but it's the same nonlinear term, so the same magnitude. And what we do is we sit or oscillator with these 2 signals, right? One with a positive amplitude and one with a negative amplitude. And of course, we don't see anything in the ancilla. And what we do is we switch off the driving potential. We don't want to keep forcing this, because otherwise you mix things on the excitation, because the excitation is nonlinear. You don't want that. You switch off your pump, and then you apply this potential. And we see that our ancilla develops this trajectory. Now, why does this oscillate? It oscillates because our lock-in is not perfectly locked at the exact frequency. We're slightly detuned, so we are going back and forth, but we get a nice initial peak with a very well-defined sign. If, to the contrary, we start with both amplitudes in the same direction, I'll tell you why this is sharp later on, then we get the exact same response, but it's going up. Now, what do we do with this response? We wait about a millisecond, and we turn on the parametric pump. And what does happen? Well, that's what happens. So if we turn on the parametric pump coming from this state, we go up to the positive solution. If we turn on the parametric pump starting from this state, we go down to the negative solution. The reason why this is sharp is because in this example, we turn on the parametric pump. In this, we didn't. I didn't realize that until I plotted the data. And because of that, when the parametric pump is on, you shift the frequency very much, and your lock-in doesn't see anything anymore. So that's why it goes down. It's not actually stopping. You just don't see it. So this is very nice, because this is an experiment. This is all experiment. So in this experiment, we are able to turn on a parametric pump to one of this kind of effective double well potential in a state that depends on the sign of the product between those 2 signals. That is the crucial operation that we need to update our system. So now what we want to do is update the weights. This is something that in a normal machine learning you would do with a gradient descent. So you would change your weights by an alpha times the gradient of the misfit. But because in our system we have binary weights, we have to follow a probabilistic update rule. So we cannot update the weights continuously because they are discrete, but we have to do it probabilistically. So what we do is we decrease the pump power to go to this area here where there are kind of random jumps. And then we apply a potential that is of the form the difference between the mode of the weight and the mode of the ancilla, which the effect that it has is to tilt out your double well potential so that it makes one solution more stable than the other. But still, this still has an activation barrier, so you have only a small probability to transition, and you can control for how long you activate this potential. So you control essentially the learning rate of your system. Here, unfortunately, is where our experiments end. But what I'll show you is the full training potential, right? So we start with the system during equilibration, and in equilibration we have this cross-care nonlinear spring between the weights in both computational modes, the gradient and activation modes, and then we apply this bias to make the weight parameterize the computation. Then we go to the update direction determination that has 2 states. The initial state, we call it the seed stage, where we apply this potential that causes the ancilla mode to be seeded with a product between the gradient and the activation, which is what we need to compute the direction. And then we apply the update, execute the update, where we couple the ancilla mode to our weight mode. So that's the ancilla mode, that's the weight mode. And we reduce a bit the power, right? The shiny means that it's being parametrically pumped. This slightly less shiny, you cannot see it by my illustrator, charge me 50 euros for it. And this has a bit of a lower pump, so it can flip. And then you end up with a weight update according to the learning rule. All right. So now this is something that we simulated. So we constructed a model. Thank you. We constructed a model for this. This is theory. But we simulate the Wanjura dynamics with the experimental parameters, or mostly realistic experimental parameters. And what we do is try to do an iris classification task. So we have our lattice, and at every corner, we apply an excitation, a sine wave, whose amplitude is governed by a feature of the flower, right? So for example, if the petal is very long, then this LP here will have a high amplitude, and so on. And we measure the output in the middle. We create 3 lattices, and we do a softmax. We define a softmax. Now, if you do this and you just start your simulation, you get 30% probability. So this is the test and training probability is where you start, you get 30%, obviously, because the system has no idea which lattice is supposed to be which one. So on average, you always get 30%. But as you keep repeating this protocol, so you apply the features, you apply the gradient of the training signal in the middle side, and then you apply the training tones, the performance keeps increasing. And what happens is that those weights are flipping. I unfortunately don't have a nice video, but essentially what's going on is that every side has a weight that is bistable. And as you apply more and more training samples, these weights flip and flip. And eventually, the system, even after about 25 training iterations, a quarter of an epoch is about 100 samples, the set, so 25 iterations. After 25 iterations, your system has essentially saturated the maximum linear accuracy that a linear system can achieve in the iris dataset. This is better than what we published in our original paper, so we're very excited in the paper because it was the first time that a learning rule gets turned into a Hamiltonian, but it was not a very good conversion. Now this one is much nicer. Now, why don't we have it? So one of the things that is going on in our setup is that if you try to, with this set of drums, until now we were going on and on with the same sample. So if you try this with this sample, all the spins end up in a ferromagnetic configuration. So this coupling couples both the computational modes, but it also couples the wave modes in the ancillaries and everything. So what we do, and it's also really difficult to connect the P modes in a way that respects the symmetry. So what we design is this type of material. It's not yet fabricated, but this is our design. In this type of material, we use a different mode, this D mode, that we can also see it in experiment. We use this D mode for computation because it makes nicer to couple them. And we use these spacer elements that what they do is they have a resonance frequency that matches the D mode, but it blocks completely the wave mode, so we don't have ferromagnetic alignment. And then we put these plates here. The middle one is for the parametric drives and coupling, and the outer ones is for the gradient determination, sign determination. Now, everybody who knows me knows I like to say something silly in my talks. I like to call this lernium. It's a new metamaterial. We call it lernium because it's a metamaterial that learns. Okay, so now how do we make the lernium? So we start with a plate that has the resonators. Then we deposit gold on it. And in a separate plate, we make the electrodes, and then you can just put a spacer of polymer and just bond it. Right? So this is something that we know how to do compared to the things that Wolfram Pernis was saying this morning. This is a game for kids, right? So this, for example, a sample that we did when I was in the lab of Sally Hoover, where we have a silicon wafer bonded with another silicon wafer, and there are also here drums that are interacting electrostatically, they're bonded and so on. So it's not a particularly high challenge. And then you can also connect them to the substrate and apply the voltages and so on. So we really think that this is something that can be done, and we hope that in the next few years we'll be able to actually demonstrate a system that solves the training problem physically without any control loop. So that's also very exciting. You could also think even of quantum versions of it, that where you don't need to do measurements to do training because the training is encoded in the Hamiltonian. Maybe that allows you to beat some limits and so on. So it's a very exciting platform to play with. So that's all I wanted to show you. I think I managed to keep it more or less on time. So thank you very much for your attention. I'll be very happy to take your questions.
Questions?
Mark, very nice talk. So could you actually even do batching with this? Sort of like add multiple error signals together before you do the update?
So I didn't think about it, but linear system, I guess. So maybe you can put them all at the same time, the whole data set. It's a very cool one. Thank you.
What comes with this? You just okay. clarify. It wasn't clear to me how you got these cubic terms from the Taylor expansion, because it seemed that they didn't converge fast enough.
They didn't converge fast enough, but that's a good thing, right? So that they don't converge fast enough.
But how do you know that the false terms,
No, they do. We kill them in two ways. So we kill them via electrode placement. So we want to place electrodes in a way that orthogonalizes your cubic term. And we kill them by frequency. So the fourth term will oscillate at 4 omega and the 3 omega and 1 omega. So this term will not be modulated for you. And the fifth one is already lower enough.
Great talk. What do you anticipate as being the biggest change when you go to experiment? Like, what is the? Do you have an idea of what
So this is experiment, huh?
But the okay, yeah.
The last one. So the last one, for small lattices, we are not super worried about localization effects because it's small enough even if it's 10 sites. For me, the biggest nightmare is a bit of a practical nightmare. That is that when you bond things, you introduce a stress, and this turns the drums into a rainbow. So this is a bit annoying to fix. We do have a solution. So if the device is like this, you can go from the back and trim the drums by depositing material. We have a machine that can do that. But it's a bit annoying. So I think a setup like this can be made to mimic the theory very well, but you will probably have to be a bit handcrafty. So to get everything with the right frequencies and so on. If the frequencies are start being noisy, the problem is if you start breaking the symmetries, then your performance kind of continuously degrades in a graceful way. So you may still be able to see some learning, but the performance is going to be worse. So I think we probably will not saturate the maximum performance of the linear case, but we still hopefully we can see quite good learning.
Awesome, thanks.
So what is the dream? So how, scaling to larger numbers or making it faster or more controllable?
Well, my big dream would be to have a chip. So those oscillators consume about an attojoule of energy. So that's the energy you store when it works. And this is, of course, a very fundamental project. But my dream would be to either train a model with a microjoule that would take a kilowatt hour in an experiment, or if we were to do these devices in photonics, train a model in a picosecond that would take a minute in a computer. That's a bit of an exaggeration, but that's the 20 years dream that I do have.
Books. So what would be a natural machine learning task for this kind of a system? I mean, it responds to acoustic waves. So you would think a problem would involve encoding, doing something on natural acoustic signals coming from space. What would be such a very effective problem?
If your goal is to build a device, so this is very fundamental. Right? Here we are really excited. The question is, how can you turn a learning rule into a Hamiltonian? And this is very fundamental. But if you're thinking about making an actual device, anything to do with speech, I don't know, a phone that learns to recognize your voice instead of the voice of someone else, that would be a thing that would be natural to do with a device like this.
So maybe some
hearing aids, a computer that you can teach. I think that would be the natural application.
The footprint of this appropriate for something like that?
I mean, that's a bit of a challenging question. These drum resonators, the device that we're building, so this is an older device, a full wafer device we're building is a millimeter square. With a millimeter square, you will not get a very high accuracy, but it's also a micron thick. So you could in principle think, oh, well, if I put 50 layers, then yes, right? There's people like Eva Weik in Munich that makes these resonators that have a pitch of one micron. And with these, you could put 1 billion of them in a centimeter. So in that sense, there is room for improvement. But this is a very practical question that we're not thinking about yet.
Okay, thank you, Marc. Let's take